In this video, we'll look at the definitions we need for hypothesis testing, and we'll look at what we need to do to set up a hypothesis test. There are many steps in hypothesis testing, and we're only going to look at the first step in this video. Here's a bit of an example so I can tell you what hypothesis test is about. A friend of yours claims to be able to guess the birth month of random strangers. And you think your friend is crazy, so you decide you want to test this claim. You're going to select 80 people at random and see if your friend can do what she claims she can do. To test her claim, we could build a confidence interval, that would work, and see if her results are different from what would happen just randomly. Alternatively, we can calculate a test statistic, either a z-score or a t-score, to see if her results would be likely or unlikely. In this video, we're just going to talk about setting up the hypothesis before we do the testing. In statistics, a hypothesis is a statement or claim about a property of the population. Hypothesis testing is then testing that statement or claim made about the population. And we might do it by an experiment, or we might test it with a survey. Sometimes hypothesis testing is called a test of significance, and I think you'll see why that's true as we go through this section. We have two different hypotheses, and the first one is called the null hypothesis, and it's denoted by H0. Null being an old-fashioned British word for zero. The null hypothesis is a mathematical statement that sets the population parameter equal to some value. We will assume the null hypothesis is true until we have some evidence that it is untrue. So this is like a jury trial in Britain or in America where a person is innocent until proven guilty. It's the exact same concept. The null hypothesis is assumed to be true unless we have some evidence against it. And that evidence that we're going to use is that test statistic that we will talk about in later sections. The other hypothesis is called the alternative hypothesis, and it is denoted by either H1 or HA. The alternative hypothesis is the opposite of the null hypothesis. So it is the hypothesis that the population parameter is different than whatever value was stated in the null hypothesis. Generally, we want to put what we are trying to conclude into the alternative hypothesis. Again, the idea is to give the other side the benefit of the doubt, to let the other side be correct until we can find some evidence against that claim. Now, there is one exception to that rule, because the most important rule for setting up the hypotheses is that equality must go in the null hypothesis. That means in our null hypothesis, we're going to have an equal sign, greater than or equal to, or less than or equal to in the null hypothesis. That is the most important rule. The other rule is that we want to put what we believe in the alternative hypothesis, but we can only do that if it doesn't contradict the first rule. Let's look at some examples. There is an online newspaper that shall remain nameless for the purpose of a YouTube video that recently claimed over 50% of Americans want more funding for our space program. I personally believe that that is incorrect, and so we want to take a random sample to test our claim that that percentage is actually less than 50%. The question we're trying to answer: can we conclude that the percentage of Americans supporting more funding for the space program is less than 50%? The newspaper claims that that percentage is greater than 50%, or put into math, that P is greater than 0.5. My claim which is going in the alternative hypothesis, is that P is less than 0.5. And where does the equality go? Equality has to go in the null hypothesis. It has to go with the newspaper's claim. Why is that so? The paper said over 50%. They didn't say greater than or equal to 50%. Why do we put the equal sign in the null hypothesis? Well, there are two reasons. One is that equality has to be in the null hypothesis for hypothesis testing to work. But the other reason we do that is, again, to give the other side the benefit of the doubt. And so it's a little bit unclear where 50% belongs, except it's not, because we have to be generous to the other position. We have to treat that like it's true until we find some evidence against it, and we must have equality in the null hypothesis. Now in the book, he writes P equal to 0.5 to remind us that we need equality in the null hypothesis. Somewhere in the fine print, he says, though we write P equal to 0.5, what we really have in the null hypothesis is the opposite of our claim. I like to write that P is greater than or equal to 0.5 to remind us of the claim that was originally made, the one that we want to disprove. So what values for P hat for our sample proportion would make us doubt the newspaper? Assume we take a sample. We get an estimate for this percentage of people that want more funding for the space program, and we're going to compare this to what the newspaper said to try to find some evidence against the newspaper. So what if the sample proportion, P hat, came out to be 55% or 0.55? Does that give us evidence that the newspaper is wrong? No, the newspaper said it was greater than 50%, so we don't have any evidence against the null hypothesis. What if our sample proportion, P hat, was 0.99? We can imagine that that would be way outside a confidence interval we might build around 0.5. That value would be really unusual. We imagine. I haven't actually done the math because this is an imaginary situation. But it still doesn't give us any evidence against the null hypothesis because even though it seems very unusual, it is still bigger than 0.5. What if we took a sample and our sample proportion was 0.495? That is less than 0.5. So now we have some evidence against the newspaper, except wait, right? This is a sample. The claim that the newspaper made was that all Americans, right, that's what they're talking about. They're talking about the population, and all we have is a sample. So that difference between 0.495 and 0.5 might just be due to sampling variability. That might not actually be evidence against the newspaper's claim. How do we build a confidence interval around 0.5 that shows us the values that would make us doubt the newspaper? Essentially, what we need now is a one-sided confidence interval. If things are unusual, but unusual on the right-hand side of the curve, that's not going to make us doubt the newspaper. Only values that would be smaller than 0.5 and unusual would make us doubt the newspaper. As with confidence intervals, we can now decide what we want alpha to be. Let's stick with an alpha of 0.05 right now, a 95% confidence interval. We only need a one-sided confidence interval. The values that would be unlikely if the null hypothesis is true are only in the left tail. Anything that's in that 95% confidence interval, that one-sided interval, could happen if the null hypothesis is true, so we don't have any evidence against the null hypothesis if our value falls in the confidence interval. The critical region is the set of all values of the test statistic that would cause us to reject the null hypothesis. And the critical value is that value that separates the critical region from the other values. So just like in confidence intervals, the critical value is what separates what's likely to happen from what's unlikely to happen. Example 1 is an example of what we call a left-tailed test because the critical region is on the left side of the distribution. Notice that the alternative hypothesis is less than, and you will see as we go forward that every time the alternative is less than, we have a left-tailed test. Let's look at another example. Let's suppose we work for an environmental group that wants to say that more than 80% of voters in the community are against a nuclear power plant that's being built in the neighboring county. Turning our claim into math, we have that P is greater than 0.8. So to put these into the hypotheses, we have that the alternative hypothesis, H1, is P greater than 0.8, and the null hypothesis is that P is equal to 0.8, remembering that the claim opposite our claim is really P less than or equal to 0.8. So the next step would be to take a sample and calculate our sample proportion and see how that compares to the hypotheses. What values for p hat would give us evidence against the null hypothesis? In this case, anything that's below 0.8 would support the null hypothesis. And so if we were to build a confidence interval, the only values that would cause us to reject the null hypothesis would be in the right tail. As before, we're going to build a confidence interval, but it's a one-sided confidence interval. The values that are unlikely to happen if the null hypothesis is true are in the right tail. So our critical region is in the right tail, and the values that are likely to happen, our confidence interval, would be on the left. Example 2 is an example of a right-tailed test because the critical region is on the right side of the distribution. And this will always be the case, as we'll see going forward. If the alternative hypothesis is greater than, that will give us a right-tailed test. Example 3. Aunt Mary Grace claims the average age of women getting married is 22, and she likes to tell my daughters this. If you're in college and not ready to get married, you are behind the curve, and that really infuriates me. I'm pretty sure that Aunt Mary Grace is incorrect. So how do we set up the hypotheses for this test? This time, we're talking about a mean and average. Our population parameter is mu, not p. Aunt Mary Grace says that mu is equal to 22, but I say that mu is not equal to 22. So our hypotheses would be that H1, the alternative hypothesis, is mu not equal to 22, and the null hypothesis is that mu is equal to 22. As before, I'm going to take a sample. I'm going to compute my sample mean x bar, and I need to know what values of x bar would give me evidence against the null hypothesis. Anything really close to 22, but not quite exactly 22, could just be sampling variability. So again, I need to build a confidence interval. But this time, anything that is too big or anything that is too small would be unlikely if Aunt Mary Grace is correct. So we've got a confidence interval in the center for the values that are likely to occur, and values in both tails that would be unlikely to occur if Aunt Mary Grace is correct and the null hypothesis is true. This is an example of a two-tailed test because there are critical regions in both tails. You will see going forward in the class that anytime we have a not equal to sign in the alternative hypothesis, that this leads us to a two-tailed test. We've seen alpha before. We know that alpha stands for the area in the tails. In this chapter, we learn that alpha is called the significance level. It is the probability that the test statistic will fall in the critical region when the null hypothesis is true. And again, like before in confidence intervals, it's connected to the confidence level. So a 5% significance level corresponds to a 95% confidence level. In this first section, we are only practicing setting up the hypotheses. Eventually, we will practice how to take the sample data and compute a test statistic and use that test statistic to see if what we found in the sample gives us evidence or not against the null hypothesis. In summary, we can use confidence intervals for hypothesis testing to see if our sample values are likely or unlikely. However, we have to be careful if we have a right-tailed or left-tailed test. In this chapter, we're going to focus on the use of a test statistic to see how far the sample values are from the claim.